They did.
And now they understand that there's a joke because I just said joke 4 times.
You guys are missing out. Sorry.
We had a joke about a banana and a towel. Use your
If
imagination.
you want to find out, come to real physics class.
They were
Yes.
separate jokes, not the same.
You must time travel to 2020, October 30th today. And it is approximately
3:35.
2
Oh, it's 2.
2:37
John's
p.m.
birthday tomorrow.
Central Standard. What?
Is it John's birthday tomorrow?
Yes, it is. He's turning 1.
Hey, October Wednesday.
Happy birthday.
He's gonna.
Remember, because it was Halloween and it snowed, right?
Yes, it snowed.
And it was so weird to me.
Yep, and I ran 3 red lights on the way to
It's
the hospital.
Halloween the same time.
Hey, we've all been there. Childbirth,
No,
am I
I
right?
have a question. I have a question. Is
Yes.
Halloween like all the...
From a single guy.
Yeah, it's always October 31st. Yep.
I mean, even other holidays or just Halloween?
That's like most holidays. Well, Thanksgiving is always a Thursday, you know. Christmas is always like the 25th. Yeah.
Okay, because I don't live for like you for
Like,
17 years.
that's a good question though, because like Easter is always a certain Sunday. It's never a number. Same with Thanksgiving. But Christmas and Halloween are always on the same number. 25th and 31st.
Number 5?
Informed that this will unfortunately fall on
I thought you only had 3.
It will. Wow.
Oh, I didn't know.
That's
I'm elected today.
that would be a deadly day. Okay, so let's get going with this. We've got just a few notes to take today.
I can see the
Name the fundamental forces of nature. Let's just see what you come up with.
Gravitational force. Net force. I don't know if that's...
electromagnetic.
Sarah came in clutch. She greeted everyone.
Strong.
Huh? Yeah.
I heard weak. I think I heard net. Any other thoughts?
Wait, nets?
I'm just putting up what I hear. These aren't necessarily right.
Oh, that's not nature.
She's like, hold on.
Fundamental forces of nature.
What's strong
fundamental forces of nature.
It was in our reading, Potter. Maybe if you would have done the chapter summary. I don't remember what they are, but I remember them there.
There are 7
Electromagnetic
sections. How can I remember all
could
7
be
sections?
combined. I did not understand that part when they were like,
Electro-
and scientists were like, and they could be the same, and I'm like, what? Okay.
That's actually the main part that I was hoping you'd remember here. So, yeah, these
We got it.
these are the main 4 fundamental forces of nature, but technically there's really just 3. Because for points where you have high particle energies, the weak and the electromagnetic go to the same value. Like if you think about asymptotes, they all kind of approach the same number at high particle energies. So technically we just have 3 forces. They call this one the electro-weak. Very creative.
And then I think I was confused because when I was reading that electroweak, I just kept saying electromagnetic. So then my brain doesn't work with words. And there you go.
It happens. But the interesting one about this is the strong force. That's kind of the newer one. It's the force that binds quarks together. When I was a kid, it was always the nuclear force. They didn't always know about quarks. So the nuclear force was the force that supposedly bind protons and electrons and atoms together. So yeah, if you remember anything about nuclear force, that one is defunct.
Mr. Hathaway. Can I
Yes.
share a random thought that entered into my head?
Yes, you may.
Electro-weak makes me think of in kindergarten when you're learning about compound words and they tried to put electromagnetic and weak together.
Yes, it does.
Isn't it? It's something, it's a made-up word.
Right, right. And it is a made-up word, you know? If I were them, I would have come up with something actually a little bit more original.
The
I
Hathaway
had
rules.
some fun
Yes.
with it.
So the other thing I want to point out is...
The Hathaways. Hathaways of life.
So we're used to talking about gravity and everything in terms of defining it like this. Force of gravity is equal to mg. But 1 or 2 problems in this section, you got to deal with defining gravity, and you treat gravity as like this field force. And all I want to do right now is just kind of run through a small, adorable little derivation of where we get this G value from. So G is yes, this is gravitational force right here. So there's a way that we can define force of gravity more specifically, because this is something that is constant if we're at Earth's surface. But if you go way above Earth's surface, what do you suppose happens to this value?
It's lower.
It gets lower because your G value gets lower. 9.8 meters per second squared is an assumption based on the idea that we're at Earth's surface. If we're not, that value either grows if you go below Earth's surface, or it gets smaller as you go above it. So if we want to define force of gravity more specifically, it would be equal to this. This is a G, mm over r squared. And on Earth, this m would be the mass of the Earth, and this r would be the radius of the Earth.
Oh, is this so that you can do other things?
Yes, yeah, because we want to be able to solve for these things on other planets as well.
Has anyone measured the radius?
Well, they've figured it out. Yep. They've got all sorts of ways to do that. But in order to use this, I just want to show you exactly where our 9.8 meters per second squared comes from. So the mass of the Earth, I should probably have these memorized by now, is 5.98 times 10 to the 24th kilograms. It is a heavy, heavy place.
That's what Ben said yesterday, where it was like if you took like 1,000,000 kilograms of weight from Earth a day, it would take like centuries or even like a millennium for the Earth to fully disappear.
Yeah.
So we have to memorize all the
No, you don't. No, these will be provided, or they're on the flaps in the book when you need them.
1,000 kilograms a second. So for the r squared thing, then like 6.3
Squared, yep.
What is squared again?
You'd have to square it again, yeah. This r is radius of the Earth, so you'd have to square it. So, if we're defining G, and we want to figure out what's going on with that overall field force, we would just isolate the G. So gravity is equal to force of gravity divided by mass. And now that we have a more specific way to define force of gravity, we can toss that in. So G and that's all divided by m, which is the same thing as multiplying it by 1 over m. With me so far? Okay. So our m's go away, and we're left with gm over r squared. So in terms of the Earth,
Now we can just solve G.
and actually G is a constant. This one I do have memorized, I think. 6.673 times 10 to the negative 12th?
I'm saying 13.
11th.
Oh,
That was close.
good guess.
So this is your value for G. And we have our values for the radius of the Earth. We have our value for the mass of the Earth. When you do all this calculation, guess what number pops out? 9.8.
So why we write this?
It's just the proof.
Because I wanted you to know how hard I worked.
Okay.
No, I
Remember when Mr. Mason made us do integrals, not integrals?
I
When
want
he
to,
made us
yeah.
do derivatives like the long way?
Yeah.
It's basically that.
so this just shows what you can do with this kind of field force. Occasionally, you might have to actually solve for this G value because you're not always necessarily going to be on Earth.
Okay.
Wanted to make sure you're aware of how that all works.
So that made a good point. How did y'all find the mass of Earth?
Actually, don't know off the top of my head.
There's a big hook on top of Earth, and they put like the hooky things. So they put like this. They put Earth on here, and then they weighed it down.
Gotcha.
That one about 5.98 times 10 to the 24.
We just went to the South Pole and put a giant scale there.
Gotcha.
Upside down.
Upside down? Yeah.
Right.
Mr. Halfway did it, of course, because he's the only one in the world. And then everybody
Yes. I did it for extra credit.
Um,